For our second topic in Unit 1, we will begin with polynomials. So what you see here is a series of these exponential terms, these little exponential expressions, and they're all strung together with minus signs and plus signs. They're added or subtracted. So what I have here is 4x to the third power minus 2x to the second power plus x plus 7. This entire expression here is a polynomial. It's made up of many numbers, many values, many terms. Each piece, the 4x to the third power, the negative 2x to the second power, the x, and the 7, each of those pieces are called terms. And each of the terms has a number out front. This one has an invisible number 1 out front. But they all have a number out front. Those numbers are called the coefficients. Coefficients are the constant factors, the number to the left of each variable, and the degree of a term is the number of variable factors in the term indicated by the exponent. So what does that mean? If someone asks you for the degree of a term, you're just going to tell them the exponent value on the variable. So in this case, the degree of this term here is 3. The degree of this term is 2. The degree of this term is 1, because there's no exponent here. There's just one value of x. And here, there is no variable term, meaning that the value of the exponent is 0. There is no variable term in this guy right here. The degree of the highest term, so the term with the highest exponent, is called the degree of the polynomial. So if someone asked you for the degree of the entire polynomial, you would just give them the highest exponent number. This is a polynomial of degree 3. And this term that has the highest exponent on it, the coefficient in this term is called the leading coefficient. So the coefficient that happens to be connected to the variable with the highest exponent is called the leading coefficient. It belongs to the leading term. So what I've written here is each of the terms, their degree, and their coefficient, just to identify them. One important note too is that just this 7, if you have a term that's just a number, that's called a constant term. Anything without a variable will be called a constant. The polynomial we looked at on the first page of this video is a very friendly looking polynomial. You'll have noticed that the terms were in order of their degree and they were all neat and in a row. Not every polynomial that we see will look all of that friendly. In order to make a polynomial look more friendly, we can use some algebra to simplify it. One of the ways we do this is by combining like terms. Like terms are terms that share the same variable and degree. So they have the same variable and they have the same exponent on the variable. To combine like terms, what we do is we add the coefficients, the numbers out front to the left, and then we state the variable. So for instance, 4y to the fourth minus 9y to the fourth, this is a polynomial, but we have like terms here. The reason we have like terms is we have the same variable in each term, and we have the same degree or the same exponent in each term. So what we do is we can add the coefficients. 4 plus negative 9, so this 9 is negative, 4 plus negative 9, and then we state the variable. So 4 plus negative 9 is negative 5, and the variable is y to the fourth power. Let's look at this example. This one's a little bit more complicated. We have 7x to the fifth plus 9 plus 3x squared plus 6x squared. I'm saying squared, that's another word for to the power of 2 if you're unfamiliar. Minus 13 minus 6x to the fifth. Now, this is in all kinds of crazy order here, right? We have a 7x to the fifth plus 9. These are definitely not like terms, okay? So there's nothing I can do to combine those. But all of these terms are just added or subtracted. Addition and subtraction, as long as we keep the negatives attached to our coefficients, we can do addition in any order that we like. So let me look for a term that is like 7x to the fifth. Here I have negative x to the fifth. These are like terms. I have the same variable x and the same degree to the fifth power. That exponent is 5. So what I can do is I can add the coefficients out front. 7 plus negative 6 is, well, that's just 1. And then I will state the variable and the degree, 1x to the fifth. I result in this term. Okay, that's the x to the fifth term. Let's see if I have other like terms. Here I have a 3x squared and a 6x squared. These are like terms because they both have an x and they are both to the second power. So I can add these coefficients out front and then state that variable and exponent. 3 plus 6 is 9, and I've stated that x squared there. Now finally I have these constant terms. Constant terms are always like terms. Numbers can always be added or subtracted. So 9 plus negative 13 is negative 4. I will state that here. So what I've done is I've taken this big polynomial and I've simplified it by combining like terms to be this friendly polynomial. You'll notice that I've listed it with its highest degree term first, its middle degree term second, and its constant term last. It's kind of a convention to put your terms in order of their degree to keep everything neat and tidy and easy to understand. Let's check out our last example here. 9w to the power of 5 minus 7w to the power of 3 plus 11w to the power of 5 plus 2w to the power of 3. Okay, I have, let's see, where are my like terms? I have a w to the fifth and a w to the fifth. Let's combine those like terms by adding the coefficients 9 plus 11. That gives me 20 w to the fifth. And my other like terms are negative 7w to the third and 2w to the third. I'm going to add negative 7 and positive 2, and I'm going to get negative 5w to the third, resulting in this new, neater, simpler, but equivalent polynomial. There are other operations we can do with polynomials other than just combining like terms. We can take two entire polynomials and we can add them together, or we can subtract one from the other. So this first example is adding two polynomials. You'll see here's one polynomial in parentheses, and here's another polynomial in parentheses. When you add these polynomials together, well, addition can be done in any order. So you can really just pretend they're stuck together. There's nothing really to be done here other than to combine the like terms among the two polynomials. So I will start with my highest degree term, 2x to the power of 3. He doesn't have any like terms. There's no other x to the power of 3, so there's nothing to combine him with. I will just restate this term here. Let's go to the next degree term. Let's see, I have a 2x squared and I have a negative 4x squared. Those are like terms, so I will add the coefficients. 2 plus negative 4 is negative 2x squared. Let's look and see if we have like terms for our first degree terms. I have an 8x and a negative 4x. These are like terms. I can add that negative 4 and that 8 to get a positive 4x. And finally, let me look at the constant terms. I have a positive 3 over here and a negative 6 over here. I can add those together. 3 plus negative 6 is negative 3. So when I've added these polynomials, I've just combined the like terms among the two polynomials to create this new, simpler, nicer looking polynomial. The next example shows you how to subtract polynomials. So we have this one polynomial here in parentheses, 10x to the fifth plus 2x to the third minus 3x to the second plus 5. And we're subtracting from that polynomial this whole polynomial, negative 3x to the fifth plus 2x to the fourth minus 5x to the third minus 4x squared. So what we need to do when we're subtracting polynomials is we need to understand that we're taking the negative of this whole polynomial. And so in order to subtract this polynomial from this one, we need to make each term in the second polynomial negative. So another way to say that is that this minus sign, the subtraction, is a negative that will distribute to each term in the second polynomial. That's what these arrows are indicating. Once we've distributed that negative over everything, then, well, this can be considered just addition of polynomials, the same as the first example. So negative 3x to the fifth. That double negative becomes a positive, so we have 3x to the fifth. I've written it down here. Negative 2x to the fourth, this guy becomes negative. Negative 5x to the third. I'm distributing a negative there, so the negatives cancel. We have a positive 5x to the third. And this negative 4x squared, when I distribute the negative, that negative cancels as well. So another way to think of this is just distribute this negative by changing the signs of each term. Once we've changed all the signs, we can just connect it with our first polynomial in an addition of polynomials type of way here. Once we've done this, we can just combine like terms like we did in the first example. So let's look for degree 5 terms. I have 2 of them. These are like terms, 10x to the fifth and 3x to the fifth. When I combine them, oh, I've rewritten it here. I didn't realize I added that extra step. 10x to the fifth plus 3x to the fifth. I've just reordered these so that my like terms are next to each other. 10 plus 3 is 13x to the fifth. Degree 4 terms. I only have one of them, negative 2x to the fourth. I've written him here, so we just carry him down. Degree 3 terms, 2x to the third and 5x to the third. I've written them next to each other here. We can add those coefficients to get 7x to the third. And then degree 2 terms, I have a negative 3x squared here and a 4x squared here, written next to each other like this. We can add that negative 3 and that positive 4 to get 1x squared. And finally, we only have one constant term, the 5, so we carry him down here. This is our resulting polynomial, written in descending order for the term degrees. In addition to adding and subtracting polynomials, we can also multiply polynomials and divide polynomials. This next page will describe multiplying polynomials. Some of this might be familiar to you. You may remember learning about this in high school under many different names. Okay, multiplying two monomials, or a monomial by a binomial, or two binomials, or foiling. Okay, all of these things describe multiplying polynomials. But I don't really like all of those terms and those different ways of teaching each separate piece, because ultimately, whenever you multiply two polynomials, it works the same way. All you need to do is you need to multiply every term in the first polynomial by every other term in the second polynomial. This works whether you have 2 terms, 5 terms, 10 terms, or 1 term. So there's no need for separate rules to memorize foiling versus monomials, binomials. It's all the same concept. So what I've written out here is multiply each term in the first polynomial by every term in the other, one at a time. What I mean by this can be seen in this example. So here's my first polynomial. It just has 2 terms, p plus 2. Here's my second polynomial. It has 3 terms, p squared plus 3p minus 2. If I want to multiply these, indicated by the parentheses just being right next to each other, I'm going to take each term in the first polynomial and multiply it by every other term. So I'm going to start with this first term in the first polynomial, and I'm going to multiply it first by p squared. Then I'm going to add to that p times 3p. Then I'm going to add to that p times negative 2. All right, that's the first term by every term. Then I'm going to take the second term and multiply it by every term in the second polynomial. 2 times p squared, I'm going to add to that 2 times 3p, and then 2 times negative 2. I've written this out longhand here below, so you can see the arrows are going to result in these multiplication terms here below. P times p squared, written right here. P times 3p, written here. So you can kind of follow along, p times negative 2, and so on, and then do the same thing with the 2 that I just described. Now, once I have this all written out, I have done the multiplication for you. P times p squared is p cubed. P times 3p, 3p squared. P times negative 2 is negative 2p. 2 times p squared, 2p squared. 2 times 3p is 6p, and 2 times negative 2 is negative 4. From this point, I have a nice looking polynomial, but I have some like terms that I can combine. So in particular, let's see, 3p squared and 2p squared, those are like terms. Negative 2p and 6p, they're like terms as well. So I've just added a step in here to list this polynomial in order, descending degree order, so that we can see those like terms a little bit easier. And then in our next step, 3p squared plus 2p, I have combined those like terms to make 5p squared. And negative 2p plus 6p, I've combined these terms to make 4p. This is my resulting polynomial at the end of that entire multiplication process. So if you're thinking back to foiling and all of those wild multiplying polynomial rules, this is really the only rule that you need to know, and you will be able to multiply any set of polynomials that you might come across in the world. It's pretty great. To show you just how great it is, I will show you some examples that look different, but the same process still applies. Here's some more multiplying polynomials. Here's one. Here's a monomial multiplied by a trinomial. But it doesn't matter, the same process works. This monomial, he's a polynomial even though there's just one of him. So I'm going to take 3x squared and I'm going to multiply him by each term in this second polynomial, each of the 3. So 3x squared times 4x squared. I'll write that here. I'm going to add to that 3x squared times x. I've written that here. And add to that 3x squared times negative 2. I've written that here. I can do that multiplication getting 12x to the 4th from 3 times 4 and x squared times x squared. I get 3x to the power of 3 when I multiply these guys. And negative 6x squared from this multiplication right here. This polynomial here is, well, it's already simplified. There's no other like terms to combine, so we are done. In this next example, my first polynomial is just a constant term. So even though he's just 7, we can think of him the way we think of a polynomial. And this you may remember as the distributive law, okay? But it's the same idea. You take this term and multiply him by each and every one of the terms in the second polynomial. So 7 times 2x cubed is 14x cubed, to the third power. 7 times 3x is 21x, and 7 times negative 1 is negative 7. Okay, our next example is two binomials. Okay, this is what you may remember being called foiling. You multiply the first, the outside, the inside, and the last. There's no need to memorize that though, just take every term here, multiply it by every term here. So I'll start with x squared, multiply him first by 2x cubed, as I've written here, then multiply him by 9, written here. Then take this 9, multiply him by 2x cubed, written here, and the 9 times the 9, written here. Okay, if I perform that multiplication, I end up with 2x to the 5th plus 9x squared plus 18x to the 3rd plus 81. And I think, what else do we have here? Oh, I've just reordered this so that it is in the descending order of the degree of each term. And that is our complete polynomial multiplication for those two binomials. Here's an interesting one next. X plus 5 whole thing squared. Remember, an exponent just means you take the base and you multiply it by itself, the number of times indicated by the exponent. So x plus 5 squared can be rewritten as x plus 5 times x plus 5. Then we can proceed in the same way as in the previous example. X times x is x squared. X times 5 is 5x. In this term, 5 times x is another 5x, and 5 times 5 is 25. Here, my 5x's are like terms, they become 10x, and here's my resulting polynomial. In our final example, we have 3x squared times 4x to the fifth plus 1, a monomial times a binomial. Take this 3x squared, first multiply him by 4x to the fifth, and then add to that 3x squared times 1. You see I've written out the multiplication here, and 3 times 4 is 12, x squared times x to the fifth is x to the seventh, and 3x squared times 1 is just 3x squared, resulting in this small and friendly looking polynomial result. For dividing polynomials, I can tell you that in this course we will only see one case of dividing polynomials, and that is dividing by a monomial, so a one-termed polynomial. When you divide by polynomials that have more than one term, things get quite complicated, and that is just beyond the realm of this course. So anytime you're asked to divide by a polynomial in this class, it will look something like this. You'll have some polynomial in the numerator on the top of the fraction, and you'll have one term on the bottom of the fraction. So in this case, x to the fifth plus 24x to the fourth minus 12x to the third is divided by 6x. To divide polynomials in this way, what you're going to do is you're going to take the one term on the bottom and you're going to put it underneath every term on the top. So you're going to kind of break up this big fraction into as many little fractions as you need to have one fraction for each term in the top polynomial. So I have x to the fifth divided by 6x, 24x to the fourth divided by 6x, plus negative 12x to the third divided by 6x. And I'm going to deal with each one of these fractions individually. So here, let's see what we can do. I have an imaginary coefficient of 1 here and a 6 on the bottom. So I'm just going to call this 1/6 so that I don't have to worry about decimals of any kind. I have x to the fifth divided by x. Remember when we divide exponential expressions, we subtract the exponents. X has an imaginary, not imaginary, sorry, it has a exponent that we can't see. So I guess you could imagine that the exponent here is 1. So 5 minus 1 is 4, x to the power of 4. In the next fraction, we have 24 over 6. 24 divided by 6 is 4. X to the fourth divided by x. We're going to again subtract those exponents. 4 minus the invisible. That's the word I was looking for. The invisible 1 here gives us x to the power of 3. Then here, negative 12 divided by 6 gives us negative 2. And x to the power of 3 divided by x. 3 minus 1 is 2, so we have x to the power of 2 here as well. All of these terms together make up our resulting polynomial after we have divided our polynomials. All of this talk about polynomials needs to be good for something. It is all going somewhere. We're going to talk about polynomials as polynomial functions in this next page. So here I've written out y equals a polynomial. Okay, now we're seeing polynomials start to look like equations. We have equal signs and something on the other side of the equal sign. Functions can be written with a y or with an f and an x in parentheses. This is a very important notation to understand. So y equals 2x squared plus 3 can also be written as f x in parentheses equals 2x squared plus 3. Now, it's important to notice that this does not mean f times x. I realize this looks like a mathematic operator happening in here, but it's not. What this notation means is the function of x. F is for function, and x is what the function is of. So x is your input value in the function, and the function is defined by the polynomial. So I've written here the function of f of x is defined as 2x squared plus 3. That is how you would read this little petite piece of mathematics right here. We can evaluate the function at any value that we like. These values that we're going to evaluate at are x values. We can plug in any number for x in the polynomial and then just evaluate the numbers with arithmetic. So if you see something like this, f negative 3 in parentheses, this, when you see this, it's stated as f of negative 3, the function with the input of negative 3. This means we're going to evaluate the function f, which is 2x squared plus 3, when x is negative 3. So, to evaluate f of negative 3, we're going to take negative 3, putting in parentheses, and we're going to plug in negative 3 anywhere there's an x in our polynomial. We had an x here, 2x squared plus 3, so this will be 2 negative 3. I've replaced that x with a negative 3, squared plus 3. From here, we just have a bunch of numbers and operations. You can follow your order of operations here. Negative 3 squared is 9. 2 times 9 is 18, plus 3 is 21. This means f of negative 3 is 21. The function 2x squared plus 3 evaluated at x equals negative 3 is equal to 21. Negative 3 is our input into the function, the x value, and 21 is our output, or our result of the function evaluated at x equals negative 3. The word function is a fancy mathematical word that has a defining property. Not any equation can be a function, but we will be dealing with functions in the majority of this class. So here's the defining property of a function. For every input value, x, there exists at most one output value, f of x. Okay, so for every input, there is at most one output. This is kind of hard to get an intuitive grasp on, but let's see if we can get some understanding. Notice on the previous page, we found out that 2 times negative 3 squared plus 3 equals 21. This is the value of the function evaluated at negative 3. Notice it was impossible for this equation to equal anything other than 21. Okay, if we plug in negative 3, we're going to get out 21 every single time. There is at most one output value, in this case 21, for this equation. And that makes this a function. Okay, so it is okay for two different inputs to yield the same output, but it is not okay for one input to yield two different outputs. This is kind of a complicated concept, but it's easier to see in a picture. Here is a graph of the function that we've been working with, 2x squared plus 3. Okay, it's not important that you recognize that this is the appropriate graph. It's just going to be a visual tool to see why this is, in fact, a function. So we plugged in negative 3, that's this x value here, and we got out 21, which is right here. So we're talking about a point right here on our picture. Okay, now there is another value that we can plug in that will also yield 21. In particular, positive 3. If we plug in a positive 3 into this function, well, positive 3 squared is still 9, times 2 plus 3 is still 21, okay? So positive 3 results in 21 as well. And this is okay. There's still at most one output value for each input value. Notice we had to input two different things to get that same output of 21. That's okay. This is still a function. One of the ways we can tell this is a function by looking at the picture is by drawing vertical lines, or imagining that we're drawing vertical lines all over this picture. There is no place on this picture where we can draw a vertical line that will cross the path of this function more than once. Okay, there's no place to draw the line where it would cross this U shape more than once. Because this is true, we know it satisfies this defining property or definition of a function. Let's look at an example that would fail to be a function. Okay, if we had some equation that resulted in the graph looking like this, where our graph was the same U shape except it was turned on its side. Well, let's see what would happen. Whatever this value is, let's say it's also 3. Okay, let's say we plug in x equals 3, and we would get out this value on the graph up here, but also this value on the graph down here. Okay, this fails the defining property of a function. Visually speaking, I can find a place to draw a vertical line that will cross this function in 2 places, okay, or in more than one place. In fact, I can draw many vertical lines on this picture that will cross this U shape in 2 places. So whatever equation created this graph is not a function. But our equation, which created this graph, is a function. What I've described here is what's called the vertical line test. It says a graph represents a function if it is impossible to draw a vertical line that intersects the function at more than one point. The final page of this video note set will talk about graphing first-degree polynomials, also known as linear polynomials, also known as lines. I realize that especially these last few pages of notes seem rather disjointed in this unit. Try to hang in there with that. What we're doing is we're laying a foundation or a groundwork for the rest of the material in the course. So although these topics might seem a little bit disconnected, we will bring them all together when we start solving functions and using all of these algebraic techniques to bring it all together. So we will, in this unit, graph a very particular kind of polynomial. We'll only be graphing one kind of polynomial for the time being, and that is the polynomial that represents a line, which is a linear function. It is a first-degree polynomial because here I've written it down, y equals mx plus b. There is no exponent on this x, so that invisible exponent that is there is the number 1. So it's a first-degree polynomial. The highest degree term is a first-degree term. Y equals mx plus b, okay, or f of x equals mx plus b. You can see it written either way. Here, the x is our variable, our input variable. Y is our output, or f of x. M represents a number, and this number will often look like a fraction. That is going to be the slope of the line. The slope of the line that we're drawing is equal to the rise over the run. Okay, we'll talk about what that means in a second. Or a change in y over change in x. So this creates a proportion that tells us how slopey our line is going to be. The letter b is also just a number. This is the y-intercept. It's the point where the line crosses the vertical axis on the graph. So here I have an example. Y equals 3/5 x plus 3. This is a first-degree polynomial. It is a linear polynomial, and we are going to graph it. So you'll notice that it's in this slope-intercept form. 3/5 is our slope, and 3 is our y-intercept. If I were to use this equation, this function in particular, to create a graph, the way I would do it is I would start with the y-intercept. I know that this is the y-intercept, so I know my graph has to cross the vertical axis, or the y-axis, at the point 3. Okay, so x is 0. I'm not traveling anywhere on the horizontal axis from my origin, but my y value is 3 right here. So I would draw a dot right here at y equals 3. Y-intercept at the point 0, 3. So 0, 3, I'm going to map that point. Then I can use my slope to find other points on the line. Okay, here's where rise and run comes into play, or change in y over change in x. It's a vertical distance divided by a horizontal distance. So this slope, 3 over 5, is telling me that I'm going to have a vertical distance of positive 3 and a horizontal distance of positive 5. So from this y-intercept, from this point here at y as 3, I can go up a vertical distance of 3 points and over a vertical distance of 5 points, and I found another point on my line. Okay, I could figure out exactly what this point is and plot it. I can also do this in the other direction, okay, by kind of, going the other way. I can go a vertical distance down 3 and a horizontal distance to the left of 5. There you go. And you'll see that -5, 0 is another point on this line. So what you can do is you can take the y-intercept point here, 0, 3, this is your x, y coordinates, kind of like you're playing Battleship, okay? And then you can find other points by adding or subtracting the appropriate x and y values from the slope. So if I take 0 and I subtract 5, I get this -5. If I take 3 and subtract 3, I get 0. And this is the point -5, 0, which is pretty cool. To show you this in the other direction, from this point, which is 0, 3, I can add my x value to the x value. So 0 plus 5 moves me over 5, okay, and then 3 plus 3 is my vertical distance here. 3 plus 3 takes me up to here. Another 3, this will be 6. So this point looks like it would be 5, 6, or a x value of 5, a y value of 6. And that is how you would graph a first-degree polynomial to create a line. There are, of course, many other ways to create this graph of a line if this slope-intercept technique is confusing to you. Remember, your x is always your input, your y is always your output. So what you can also do, if you're feeling stuck and you want to graph this equation, is you can input values for x, whichever values you choose, and see what comes out for y. Then you can just graph these points on your coordinates and connect the dots. You'll see that they will connect to form a line as well. I've attached some supplemental resources to show you some other ways of graphing lines, but I really think one of the best ways to kind of figure this out is to play with a bunch of examples yourself in MathXL.